Good afternoon. Thank you for coming for the second session. The first talk will be by Professor Gentaro Watanabe from Zhejiang University on quantum performance of microscopic thermal machine under outcoupling. Okay, thank you.
So I would like to thank organizers for giving me this great opportunity. And this talk is based on the collaboration, mainly with Prasanna from IIT Gandhinagar. And the other collaborators are Peter from Augsburg, and Myung-Jun from the Duke Kunshan University, and Adolfo from the University of Luxembourg. So the main topic of this talk is about the thermal machines outcoupled to the external system. So I would like to briefly introduce the motivation and background beginning. And then we mainly focus on the performance of such kind of micro machines in the operation over multiple cycles and by multiple engines. And then if time allows, I would like to briefly introduce our recent results about the charging assisted by the dephasing. So that we are discussing the heat engine, which is usually this kind of microscopic machines. However, technological advancement allows us to downsize to make the engine using the small system as a working substance. So here, small means a number of degrees of small. For example, nowadays people can realize the heat engine using the single macromolecule like this, or even single atom like this. And then in this talk, we discuss the quantum heat engine. This quantum heat engine, by definition, is an engine using the quantum system as a working substance. So that, for example, this quantum system can be cold atomic gases, cold quantum gases, or say two-level system, etc. So the main incentive to consider such kind of system is people expect we can improve the performance using some quantum resource which is not available for the classical case. And then this program actually initiated more than 60 years ago, but it is a very old problem, but still many people are interested in. And then recently, due to the fabrication of the quantum heat engine in the experimental setup, people are more and more interested in it. So the grand motivation for the quantum heat engine, first one is a practical side, and the second one is a fundamental side. Regarding the practical side, by considering the quantum heat engine, by studying the quantum heat engine, it is actually makes a way to realize the small refrigerator. And then this small refrigerator is very important, especially for the removing the heat in the quantum computer and so on, as advocated by the Ronnie before. Regarding the fundamental side, the study of the quantum heat engine actually helps us to understand the quantum thermodynamics. For example, if you consider the Carnot cycle, role of the Carnot cycle in the classical thermodynamics, it really has an important role. We expect similar role is played by the quantum heat engine in the quantum thermodynamics. So that when people study the quantum heat engine, people are interested in so-called the quantum thermodynamic signature, which means the quantum effect in the thermodynamic quantities. So one of the main strategy to find this kind of quantum thermodynamic signature is to consider so-called a many-body quantum heat engine, where the people can use the quantum coherence of the working substance to enhance the performance of the engine. Recently, people also try to consider some interaction-driven quantum heat engine, where the external parameter is interaction strength. And then using this knob, people can change the equation of state and also statistics of the particle. Another route to find the quantum thermodynamic signature is measurement-driven quantum heat engine, as proposed by the Alexia. So here, for example, one of the say, thermal strokes is replaced by the quantum measurement, and then you can drive the say, thermal machine partly using the quantum measurement. But what we are going to go is a third route, so-called outcoupling. So the outcoupling means we consider the external system on which engine does work. So the usually assessment of the performance of the quantum heat engine, people consider a single engine through a single cycle without coupling to the load. However, if we consider the actual operation of the quantum heat engine, then quantum heat engine has to be outcoupled. We have to couple to the load, external system on which engine does work. And moreover, quantum heat engines are very small, therefore it is susceptible to the outcoupling. Therefore, it is important to consider the performance under the outcoupled condition. So our problem setting is like here. Here you can see that we have the engine, and then heat bus coupled to the engine. And then this combination is so-called the work resource. But in addition to this, we explicitly consider the external system on which engine does work. Here we mainly consider the cyclic heat engine. Therefore, Hamiltonian of the engine part, coupling between the engine bus, coupling between the engine and the external system, they are periodic. On the other hand, the Hamiltonian of the bus and the Hamiltonian of the external system, for simplicity, we consider this is time independent, which means there is no time-dependent external parameters. So the main issue of this study is as follows. If we consider the say, performance of the quantum engine, it is usually assessed by the single cycle, by a single isolated engine. But under this assumption, under this common strategy, there is a common assumption, which means work done by the multiple engines in multiple cycles is proportional to the work done by single engine in single cycle, like this. And then what we want to challenge is whether this assumption is really true or not. So what we are going to challenge is to this kind of conventional approach by considering the operation over multiple cycles or by multiple engines, and by explicitly considering taking account of the external system on which engine does work. Through this study, what we have found is actually the performance of the heat engine should be assessed for the global process over multiple cycles by multiple engines, which means more specifically, you have the intercycle coherence and the collective effect, and then due to this effect leads to the enhanced performance. It is possible to have some enhanced performance by this effect. So I want to discuss this issue more in detail. So the first, I will talk about the performance over multiple cycles. So now we consider the following setup. So that there is an external system on which engine does work. And then to study this one, we introduce the two definitions of the work. So the first work, WT, is we perform an energy measurement on this external system after each cycle. So after one cycle, first cycle, we perform the energy measurement on the external system. After second cycle, we also perform the energy measurement. And then we repeat this one n times. And then we can also evaluate the total work amount by these n cycles. Second definition of the work, W, is as follows. We only perform the energy measurement at the beginning and then after n cycle. So that in the middle, we do not perform any energy measurement on the external system, and then we can evaluate the work by these two results. In the classical system, of course, these two definitions are basically, there is no difference, but in the quantum system, due to the quantum measurement back action, we have large difference. The average of work through the n cycle for the first definition and the second definition can be written like this. This T is a transition probability from the initial 0 state to the final I state. And then this transition probability can be consists of the backward branch here and then the forward branch. And then this K vector is a vector which represents the intermediate state after each energy measurement, after each cycle. In the case of the first definition, we perform the energy measurement after each cycle. Therefore, the intercycle coherence is killed. Therefore, this K vector for the forward branch and backward branch should be the same. On the other hand, in the case of the second definition, we do not perform this intermediate energy measurement. Therefore, it is not the case. So that there is an intercycle coherence in the second definition. And then, due to this intercycle coherence, we can actually enjoy some enhanced performance. To demonstrate this one, we have to set the system, detailed system, and then also the engine protocol, and then also coupling protocol, so that we have to set each of them, and then to evaluate the work enhancement. So that, for example, for the external system on which engine does work, we take the harmonic oscillator, and then for engine, we consider the two-level system. Here, this omega t is a time-dependent parameter, which we sweep externally. And then for the coupling between the engine and the external system, we consider some dipole coupling like this. And then we assume the initial state of the external system as the ground state. Regarding the engine protocol, we take the quantum Otto cycle protocol, which consists of the two adiabatic stroke where we do not have any coupling with the heat bath during this process. And then two isochoric process where we have the contact in the thermal bath, but there is no contact with the external system. Here, in the two adiabatic strokes, we assume that parameter drive is slow enough. And then we also assume that after the two isochoric stroke, we assume that there is a perfect thermalization equilibration. Regarding the coupling, we consider two cases. One is an impulsive perturbative coupling like this, which allows us to get some analytical result. But we also consider such kind of smooth continuous coupling where the strength is no longer perturbative, and then also the coupling is almost always turned on, which is somewhat opposite limit of the perturbative and impulsive coupling. So that we consider these two. So the result is as follows. The left panel is for the impulsive perturbative coupling, and then the right panel is for the continuous non-perturbative coupling. The main feature is almost the same. So here, vertical axis is the average of the work, and then the horizontal axis is the number of cycles. First definition of the work, where we perform the energy measurement on the external system after each cycle, we have the linearly increase with respect to the number of cycles, of course. On the other hand, in the case of the second definition of the cycle, definition of the work, we have oscillatory behavior like this due to the intercycle coherence in the external system. Therefore, work done in multiple cycles is not proportional to the work done in the single cycle. And then, if we look at some optimum number of cycles here, this red one actually surpasses the black one, so that we can get the enhanced work output here. Furthermore, if we perform the energy measurement at optimized interval of cycle, for example, once per 10 cycle, then actually we can get this linear dependent, stroboscopic linear increase with the enhanced slope. Therefore, this means that we get the quantum enhanced work output by optimized interval of the quantum measurement. It is also interesting to introduce some, dephasing on the external system. So here, we put some dephasing on the external system on which engine does work. Here, I show the result as a function of the number of cycles. This black one is actually the result of the second definition of work without any dephasing. And then this red one, straight line, is also the first definition of the work without any dephasing. And then this blue, purple, green is say non-zero dephasing. Here you can see that if the dephasing is very small, then it starts to deviate from the second definition of the work. And then finally, if the dephasing is very strong, then it approaches to the first definition of the work. But interestingly, in the intermediate strength, we have some enhanced performance, which corresponds to the, which is similar to the situation with the optimized interval of the quantum measurement. So that we can say that moderate decoherence can enhance the performance. So then in the second issue is about the quantum performance by the multiple quantum heat engines. Sorry. So now we want to consider an ensemble of the multiple identical heat engine, and then ask what if these engines are indistinguishable. Of course, if we consider this kind of macroscopic entity, it doesn't make sense. However, it makes sense if we consider each engine consists of the, say, like a single atom like this. And then what we have found is due to the, if we consider the ensemble of the indistinguishable bosonic identical engine, and in this case, due to the permutation symmetry of the ensemble, we obtain the collective enhancement of the work output, which is genuine quantum effect. So let me discuss a bit more detail. So the setup is as follows here. Similarly to before, we consider the engines outcoupled to the external system, but now we have multiple engines here. And then external system and on which engine does work is common. And then we consider each engine consists of the two-level system, but now I have the multiple two-level atoms. And then the engine Hamiltonian can be written like this using the spin operator here, SXSZ. And then in the case of the indistinguishable engines, this SXSZ can be written in terms of the Schwinger representation using the annihilation operator of the ground or excited state. On the other hand, in the case of the distinguishable case, this SXSZ operator can be given like collective spin. By assuming that initial state of the external system as a ground state, then the average of the internal energy change can be written in terms of the probability at which I have the ith energy state of the external system. And then this PI probability can be written in terms of the, using the two-time correlation function of the coupling operator in the engine degrees of freedom. If we consider actually the impulsive type coupling, then this quantity can be simplified, and then we can separate the factor which depending on the engine degrees of freedom and the external system degrees of freedom. So that this part is actually same for the indistinguishable or distinguishable engine. Therefore, if we want to discuss the quantum enhancement due to the distinguishability, we can just focus on this first factor here. And then actually, we can show that if we consider the slow driving limit, this factor for the indistinguishable case is always bigger compared to the distinguishable case if the number of particles is equal or bigger than 1. Therefore, we can say that there is a quantum statistical enhancement which is characterized by the ratio between the indistinguishable case and the distinguishable case. brief explanation of this quantum statistical enhancement comes from the difference in the Hilbert space. So that if we consider the statistical indistinguishability, then actually the number of allowed states are quite limited. If we consider the distinguishable case, we have 2 to the n states. On the other hand, in the case of the indistinguishable case, we have only symmetrized states, therefore only n plus 1 symmetrized state. Due to this strict constraint of the Hilbert space, we have the collective nature in the indistinguishable case. So let me demonstrate using some specific setup. Same as before, we take the harmonic oscillator for the external system, and then coupling is a dipole type coupling. And then engine is a 2-level system, and then they work as a quantum auto engine. So here, quantum enhancement parameter as a function of the number of engine, it is always bigger than 1 if we consider the impulsive coupling. So that we have actually the quantum statistical enhancement. We also consider the continuous coupling like this. And then here I show the, this parameter plot for the quantum statistical enhancement parameter is bigger than 1 or smaller than 1. This gray part corresponds to this epsilon is bigger than 1. Therefore, we have quantum statistical enhancement. So here you can see that if the number of the engine is small, but not so large, then almost all regions of the parameter, actually, we have the quantum statistical enhancement, which is important because the number of, this is more relevant situation for the near future experiment. Actually, if so far we just focus on the increase of the internal energy of the external system, therefore, but this increase of the internal energy of the external system consists of the several contributions. One is a heat conduction from the working substance to the engine. Second one is a work purely by the turning on and off the coupling. And then third one is actual work output by the action of the engine. And then actually the third one is most interesting or more relevant quantity for us. And since time is limited, I do not explain in detail, but actually we estimated that this third contribution also shows the quantum statistical enhancement. So the remaining 3 or 4 minutes, let me briefly explain our recent work, recent result about the charging problem of the quantum battery connected to the charger. So here is a setup. I consider the battery, and then it is connected, outcoupled to the charger, and then this charger is driven by the coherent drive. And then we also consider this charger is subject to the dephasing here. This coupling Hamiltonian satisfies like this, which means the coupling Hamiltonian conserves the local Hamiltonian of the charger plus battery part. And then we study the charging problem using this Lindebrand master equation. Main result is as follows. So that if we have the small dephasing, weak dephasing, then there is an underdamped oscillation, and then it takes a long time to stabilize this charging. So the vertical axis is the energy of the battery, and then horizontal axis is the time. So that what we want to do is we charge up this external, we charge up the battery as quick as possible and as stable as possible. So that if the gamma A is small, it takes a long time to stabilize. On the other hand, if the gamma A is too strong dephasing, it also takes very, very long time to reach the asymptotic value. Therefore, there is some moderate optimum gamma A, which leads to the fast stabilization to the asymptotic value. So the presence of this optimum gamma A comes from the competition between the underdamped coherent oscillation and the quantum Zeno effect. When the dephasing is very weak, we have underdamped coherent oscillation. On the other hand, if the gamma A is very, very large, then we have the quantum Zeno effect, where the, say, charger state is projected or stick to the, say, eigenstate of this state. Therefore, we have very, very slow energy flow to the battery. Therefore, we have the optimum gamma A. This kind of dephasing effect is somewhat similar to the shock absorber in the car. Here, shock absorber, basically, they want to, say, absorb the shock and then relax to the equilibrium state as soon as possible. So that this, say, moderate dephasing works something similar to the optimum shock absorber. So let me summarize my talk. We consider the performance of the outcoupled quantum heat engine, and then focus on the effect of the multiple cycles and the multiple engines. What we have found is work done by multiple engines in multiple cycles is not proportional to the work done in the single engine in single cycle. Regarding the multiple cycles, there is an inter-cycle coherence in the external system, which leads to the, say, oscillatory behavior. And then we can actually get the enhanced work output by, say, optimizing the interval of the quantum measurement. Regarding the multiple engines, we have the quantum permutation symmetry of the indistinguishable bosonic engine. And then this leads to the quantum statistical enhancement of the work output. Finally, we study the charging of the battery coupled to the charger, subject to dephasing. And then we found that moderate dephasing of the charger actually enhanced the charging performance. So this is all, and thank you very much for your attention.
Thank you, Gentaro. Any questions? Okay. I will start with the first question then. If you go to the last portion, if you show the graph, it's a very naive question. So when you look at the charging with different gamma alpha, okay, why can't I stop at 17 for small gamma alpha and charge the battery there and I stop there?
Oh, sorry. So that this one is actually the battery is, in this specific calculation, we consider the two-level system as a battery and the two-level system as a charger. So that if we consider the, for example, harmonic oscillator as a battery, then it goes, say, overshoot. I mean, it increases monotonically.
Yes, question over there. Thank you.
Hi, thank you for the nice talk. So I have a question about when you explain the advantage of using indistinguishable versus distinguishable particles, you have this explanation with saying that if you have, in the distinguishable case, you have 2 to the power n possible microstates, whereas in the non-distinguishable case, only n states. Mm-hmm. Does that mean that you add a renormalization by hand afterwards, or it comes out directly from the equation, this advantage of the indistinguishable states?
Sorry, I'm not, could you?
So
could you repeat your
maybe
question?
you can go back to the slide where you had these. Yes, here. Okay. Does it come out directly from the equation, from the way you compute those delta U, etc., for the 2 cases, that you have an advantage, or do you have to add by hand a renormalization based on this argument here, that you have 2 to the power n states in the one hand and n plus 1 states on the other hand?
Oh, so that this nature is automatically implemented if we consider the, say, situation with the indistinguishable engine. Mm-hmm. Hilbert space is automatically, say, limited. So this is actually the direct consequence by considering the, say, indistinguishable engine.
Okay, so there is no, it's all okay from the start, you don't have to add this normalization at the end?
No, we don't have to. Yeah.
Okay, yeah. Thank you.
But of course, if we consider the, say, even if I have the same setup, but say we have very, very strong decoherence and so on, mm-hmm. then each engine can be distinguishable. So how to say? In this case, we assume that there is a perfect, quantum indistinguishability, mm-hmm. which allows us to have all the engines are indistinguishable. Mm. Is it fine?
Okay,
Is it
okay,
clear?
yes, I mean, maybe we can talk later.
Yeah,
but,
yeah, yeah. So that we can also consider introduce some decoherence. For example, if I have the very high temperature, then the say wave packet of the each engine becomes small and small. Then actually in reality each engine can be physically distinguishable.
Okay, so, I see. Okay, thank you.
Okay, thank you very much. Let's thank Gentaro again, and we'll move on to the next speaker.